This is the video recording for homework 6 of probability and stochastic process. We first discussed the first problem. We are given an x and y joint density function given by f(xy), and it's equal to a1 plus x times y over a, with x and y, with absolute value of x and y less than 1, and the function is 0 otherwise. So we need to find out for the first question, find out a, so that the above defined function is a valid joint density function. For a function to be a valid joint density function, we have to know that the integral of this density function should be equal to 1. So we can derive the function into this form. We take the x and y from -1 to 1, which are exactly their value domain, and take the integral of the density function with respect to x and y. And this we can get, first we calculate the integral of x from -1 to 1, and we can get the equation like this: integral from -1 to 1 with 1 over a times bracket 1 plus y over 2 minus the sum of -1 and y over 2, and we take this integral of y of this equation, and then we can get 4 over a equal to 1, and thus we can easily get a is equal to 4. For the second question, we are to find whether x and y are uncorrelated. And since we have concluded from some theorems from the course lectures, the first is if x and y are uncorrelated, it's necessary and sufficient condition is C, the covariance of x and y is equal to 0, or the value of e of x times y is equal to the expansion of x times the expansion of y. So if we can find out this equation, we can directly prove that x and y are uncorrelated. So we try to find out the value of these equations. The expectation of x times y is integral of xy times the density function of fxy. Thus we can get it to be ultimately 1 over 9. And we find the expectation of x, it is equal to the integral of x times the density function fxy, and finally we can get it to be 0. And we find the expectation of y, it's equal to the integral of y times the density function fxy, which is ultimately equal to 0. So we can easily see that the expectation of x times y is equal to 1 over 9, which is a number, not 0. But the result of ex times ey is exactly equal to 0, which are not equal to expectation of x times y. So we can get that x and y are not uncorrelated. For the third question, we have to find if x and y are independent, and we have found a few theorems from the course lectures. The first is if x and y are jointly normal and uncorrelated, we can get it's the sufficient condition for x and y to be independent. And if x and y are uncorrelated, it's the necessary condition of x and y to be independent. And since we have already derived from the second question that x and y are not uncorrelated, so of course x and y should not be independent. For the fourth question, we have to find the joint density of x squared and y squared, and we can do this by introducing auxiliary parameters. So if we take z equal to x squared and w equal to y squared, we can find the Jacobian to be j equals to 2x 0 0 to y, and the Jacobian value actually here should be the absolute value of j, and it's equal to 4xy. And actually from these two equations we can actually get 4 different sets of solutions which are listed here. And so the density function of zw should exactly be the sum of fxy with values of each solution set over the absolute value of Jacobian to the second degree root of Jacobian, and to the absolute value of Jacobian with taking it at a second root. And so we can write it as here listed above, and we can see the next page for the results. When z is between 0 and 1, and w is between 0 and 1 as well, and we can derive the former equation to be actually expand it to be like this, and get the equation to be 1/4 times the root of z and the root of w. And so when the z and w are taken as values other than this domain, we can easily see that this density function has does not exist, and z and w has no solution. So we have to take the density equals to 0, which means that z and w are independent from each other, are not independent from each other at this point. And so we can get we can write it as fzw is equal to 1/4 times root of z and the root of w. And we can see that if we divide it into two parts, the first part is 2 times the root of z, and the second is 1/2 times the root of w. We can see that these two are different density functions which satisfy the condition that fzw equals to fz times fw. And we can also get it if zw is equal to 0 otherwise. So we can prove that for the joint density of x squared and y squared is exactly this, but only denoted in z and w here. And for the fifth question, we are to find the to prove that x squared and y squared are independent, and as I just described in the fourth question, and the density function of z and density function of w can be written as here when z and w are chosen the values appropriately. And we can see that fz times fw is exactly equal to fzw, which indicates that z and w are independent, which means that x squared and y squared are independent. So here's the finish of this video.